Questions on anything so far? But you know everything, absolutely everything. Which one? The chart or the graph? Yeah, that should, yeah. Okay, so that one is 1 to 20.
Oil rig.
All right. What's your preference of substrate for glycolysis?
Glucose.
Right. Good.
Yeah, you think better.
What is If anybody doesn't want to stay with it, this is voluntary, guys. I know some people are probably pretty sure of it, so don't worry about it. Very much we'll see. All right. So now what have we made? We gone all the way around Krebs, right? So what have we done to our poor little glucose molecule?
Turn it into
ATP.
H2O.
It's been fully oxidized to CO2 and water. We've created 10 ATP. How many NADHs? How many NADHs? 6 in Krebs, right? And then 2, and then 2, so 10, right? 10?
No, it says 6 here. Yeah.
No, from the beginning to all the way through Krebs cycle. So, should be 10, right? 10, okay. Phew. Make sure I can pass this test.
And what?
10 NADH.
10
and
total.
2 FADH2s. Right, that's what we got out of this whole thing. All right, now, what do we have left over to do? You got a whole bunch of those electrons you've been shelling around, right? So you're going to send those to the electron transport chain. This is where you're going to make the most bang for your buck. Okay, so what do I want you guys to know about this part? Few things, I'm not going to worry, I don't really care about people memorizing ubiquinone, cytochrome D, cytochrome C1, cytochrome C, cytochrome A. You do research later on, you have to work on cytochrome C. So which one? Good, so let's walk through it one step at a time. You're going to do this, you have a bunch of, you brought all these electrons down here. And in prokaryotes, you're going to be in the cell membrane right here, and then outside the exterior, you're going to set up this gradient. In mitochondria and eukaryotes, it's going to be inside of those sister ring, right? You're setting up a gradient. NAD comes down here from glycolysis, right? NAD now drops off its hydrogen, its proton, its electron. So now has it been oxidized or reduced? We're going from
Oxidized.
NADH back to NAD+.
And oxidized.
Now it's been oxidized. Good. So the proton gets pumped across into this space, and the electrons go bouncing down these proteins in the membrane. Really all I want you guys to know. FADH comes down, it's been oxidized or reduced.
It's being oxidized.
It's going to be oxidized. It's going to drop off its 2 protons and 2 electrons. Protons are going to get pumped through here. Electrons are going to bounce down here eventually. What you're doing is you're setting up a what on the outside? A gradient, electrochemical gradient, right? A proton gradient. You got way more protons on this side than this side. It's got a plus charge. Also, what's happening to the pH out there? Going up or down? What is the pH?
Up.
Down. Up?
Up.
Down.
down.
Wow.
Becoming more acidic,
pH
right?
down.
What does pH stand for?
Power of hydrogen.
It's the inverse log of the hydrogen ion concentration. Whew.
What?
Yeah. That's what it stands for. What that means is, how many of these little bad boys you got floating around out in the environment? Now, that's what it means. So the more of those you got, the lower the pH is going to be, right? Wait. So now, as you're bouncing down here, you set up a gradient. Okay? This gradient now, the electron's going to bounce down here and get shuttled out down here. This gradient's set up, but you have this enzyme called ATP synthase. Okay? And it's kind of like, remember the old-fashioned water wheels you see in the old mills? They would spin when water went through and they would turn something and they would make something. That's all that's going on here. It's not flour, it's ATP. As the protons go down this gradient, this thing spins and it takes ADP and inorganic phosphate and it makes what? ATP. It's just substrate level phosphorylation. Is it taking this phosphate off of anything? No. This is what? What's the other one? Oxidative phosphorylation. And the reason they call it that is it gets its energy, this proton motive force, the proton's moving from a bunch of redox reactions. And that's why they call it oxidative phosphorylation. Right? So you got a whole bunch of ATP. Now you brought your electrons down here and your hydrogens. But what are you going to do with those? You just going to hang out inside of your mitochondria, inside of your cell? What's that going to do? Got a lot of problems. Okay? You messed up everything. Why do we breathe oxygen? What's the only reason we breathe oxygen for?
Vital electron.
That terminal electron acceptor, right? Right here. Terminal electron acceptance. Oxygen comes in, it combines with the hydrogens. Oxygen plus hydrogen equals water. It's called metabolic water. Okay? You actually make water in there. So now you've gotten rid of the hydrogen ions and made water, and you made a bunch of ATP. Everything should be doing what? Nice and happy. These are taken care of. You don't have a bunch of hydrogen ions floating around anywhere. You completely combusted that glucose into what? Carbon dioxide and water.
Ah.
All right. And they can trace this, like I said before. If I took carbon, glucose, and I radioactively labeled one of those carbons in the glucose, where would I find that radioactive carbon? Where's the first place it would show up? Right here, that carbons are radioactive. What's happened to those carbons as we go down to their respiration? Where do we get rid of them? What do they get transformed into? Okay, let's look. Do we have any carbons missing in glycolysis? Started with 6. How many do we have down here? 6. Nothing there. All right. Started with 6. So 3 times 2 is 6. So we still have 6 here, but what do we do here? Pull off a carbon, make CO2. If that carbon is radioactive from glucose, that means this CO2 is going to be radioactive, right? Now we come down here, nothing else. Now we go into Krebs. Those 2 are radioactively labeled too, right? As you move around the Krebs cycle, where do you lose the carbon? Right here and right here. They've been put into CO2. So if I have radioactive glucose, and they can do this, they've given it to mice, and they eat it, and then where do you find that radioactive? What shows up radioactive first?
Good one.
We inhale oxygen, right? We exhale what? Where did that carbon dioxide come from? cellular respiration. So if the radioactive glucose goes through cellular respiration, it's turned into CO2, where's that CO2 gonna go? You actually exhale it. And they actually can do that. They can actually trace it. I give them food, they'll eat it, and they can look at their breath. Kind of hard to get their little mask in their little mouth. And they can actually detect the radiation coming out of it. All right. So, what are we made from? The next important part. What have we done here to these NADHs? We oxidize or reduce them. Oxidize them back into what?
NADs.
You know what?
NADs.
NAD. Now what do I do with them? They just go on vacation? Where do they go?
Glycolysis.
Good. Back up to glycolysis because you have to what? You have to regenerate your NADs. Otherwise you don't have, you want to keep making an endless supply of NADs for glycolysis. No, that would be stupid, right? They would waste energy, you'd have a buildup of NADs. So these are, remember I said think of them as what? Think of them as Uber for electrons. They pick them up at glycolysis and they take them to where? The electron transport system, and they drop them off. Now it's going to go right back up to where? Glycolysis and pick up what? More electrons. So you have to regenerate them. If you quit getting oxygen, this pathway shuts down because you have to have that terminal electron acceptor, otherwise things get really bad inside of the cell. So what do you do now? You just die? Well, we do, but let's say you're a yeast. Are you just gonna die? No, you can still make some energy. You can still go through fermentation. But what do we do? Right back here, fermentation is gonna be like glycolysis. But what do we need right here?
NAD.
You need NAD, because if you don't make NAD, you're not gonna what? You're gonna stop that pathway so you can't make those 2 extra ATP. So you've gotta have those NADs. If you don't regenerate them during the electron transport system, what can you do? And that's fermentation. Okay. So fermentation, let me go through it.
No NADs use cause fermentation.
So sometimes cells cannot completely oxidize glucose by cellular respiration. Cells require a constant source of NAD. You regenerate it in cellular respiration. Cannot be obtained simply by using glycolysis and Krebs because you're doing what? You're actually using those up, right? So the fermentation pathway provides cells with an alternate source of NAD. Partial oxidation of sugar to release energy using an organic molecule that's already inside of the cell. So in this case, if you're a yeast, you're us, pyruvic acid is going to be NAD is oxidized or reduced here.
Oxidized.
Oxidized back to NADH is oxidized back to NAD, right?
Right.
That means pyruvic acid has been reduced. Prove it to me. For extra credit of the test, prove it to me. Oh, my TV's come back. Sorry, guys. Sorry about that. How do I know that's not oxidized and reduced? Hey, I say, well, because that's NAD and I lost that hydrogen, that electron, where did it go? Methyl group, double bond oxygen, double bond oxygen, hydroxyl group. So what do I move?
You moved it to the second carbon.
This hydrogen came down here, get rid of that double bond and make the hydroxyl group. So now, that proves to me that molecule has been what? Reduced or oxidized? Reduced.
Because it gained. It gained.
Reduce the lactic acid. If you're a yeast, pyruvic acid goes down, you decarboxylate it, you give you acetaldehyde, and now NADH is going to be reduced or oxidized. Oxidized back to NAD, and acetaldehyde is going to be what? Reduced to ethanol. And guess what happens in your liver? To the
That's
ethanol.
where alcohol gets processed.
They come in the reverse of that. We actually turn it back, you eventually turn it back into acetate, acetaldehyde. Aldehyde dehydrogenase, and then you don't want acetaldehyde, so you have alcohol dehydrogenase, because you acetaldehyde, and then acetaldehyde broken down to acetate. So the reverse. All right. Everybody got that? That wasn't real convincing. You have to have NADs to even get through glycolysis, right? Because if you don't, you can't get those last two ATP you need. So you're just going to be spinning it, right? Spinning your wheels. If you can't regenerate the NADs through electron transport system, you have an alternate pathway, fermentation.
It does cause fermentation.
You can go this way. So now you take that pyruvic acid and you reduce it to something else. So you oxidize, you get rid of those electrons, right? So now NAD can go back up to where? The beginning, and you can at least make how many ATP per oxygen? Per glucose? 2. Can we keep going on 2 ATP per glucose? Not very long, right? Otherwise we couldn't suffocate ourselves, right? Yeast, they don't have a problem with that, they can keep going.
How does a yeast or bacteria decide to go through fermentation or through cellular respiration?
Same thing, oxygen deprivation.
So if they're like an environment where there's plenty of oxygen.
It's gonna be which one's more energetically favorable.
Okay.
Right, and that's a good point, we get to this later on, talk about anaerobic fermentation. They turn genes on and off to do it. So, if you're a yeast, why would you pick, which one would you, how do you pick which one to go through? And preferentially, it's gonna be cellular respiration. So when oxygen drops and that pathway shuts down, then you'll shift to fermentation. Okay. And if you don't believe me, what's bleeding off here, right here? You get ethanol and what? CO2, right? Anybody here ever made beer? What? Have you ever seen brewing beer? If you look at beer while it's fermenting in a little tank, there's all this foam on the top, and that's the CO2 bleeding off from fermentation. So in case you don't believe me. I don't know, I may try and do it, maybe I'll see if I get permission, maybe we can make some beer in here for a while.
Someone made a beer out of their spit.
No, that's called,
Because of the enzymes that are in your spit, so this one beer maker got all the employees to chew on something and they spit it out and they use the spit, and since it boils, or they use something that, I don't know, they use the enzymes in the spit to make beer.
what do you ever, it's called pote? You ever heard of that? Pote? The pote, anybody heard of pote? Down in the Amazon rainforest, several different indigenous tribes, they make a fermented drink by doing that. They spit it. There's different names for it. My little brother drank some of that one time when we were down there.
That's so
They got cholera. What usually happens is the yeast are gonna outcompete the bacteria and everything else. So yeah, I'm not gonna buy somebody pay good money for somebody's spit. Are you serious? They actually marketed that?
You can see it on YouTube, it's on
Wow.
YouTube.
All right. Maybe I'll see if we can make some beer in here. We did UTEP, they used to do it at microbial physiology. Does anybody ever teach us that at UTEP? Dr. Jones was there, the first lab period, you set up your beer, you made beer. The last lab period of the class, you drank your beer. Pretty cool. They got really a lot more strict on. They got a lot more strict on that, so I don't know. Secondly, you have to be very careful about, I don't know how they get away with the whole 21. Drinking anything on that. Anybody here not 21? All right, NADH is oxidized or reduced.
oxidized.
Oxidized, that means pyruvic acid is reduced. If you're clostridium, you get acetone, we went over that. All right. Okay. Just know And what is, don't forget this term right here. Chemoosmosis. Chemoosmosis is just that whole thing of making ATP by using that proton gradient and everything else. The whole pathway is called the electron transport system. The actual process is chemoosmosis. So cells use electrochemical gradients to generate ATP. All I really guys want you to know about this whole thing is these pathways are reversible for the most part. You can take fatty acids, you can take triglycerides and a lipase, which is also going to be like amylase. Lipase, you can cleave off the glycerol. You can dump that 3-carbon sugar back into where? Phosphorylating, you stick it right back into glycolysis, it can work its way all the way down, right? You can take the fatty acid tails and you can beta oxidate them, and you can get boom, boom, boom here. You can throw these into where? And you pull
Electron
these
transport
off,
chain.
you're making FADHs and NADH2s, and you can get what? Acetyl-CoA and put it into crepes. You can also do the reverse of that, right? You can take out DHAP and you can pull it back through and make your glycerol out of it. Same thing with the proteases. You can cleave them with proteins with proteases, deaminate them, and that leaves you what? That looks kind of familiar, doesn't it? Throw that right back into crepes now. Anabolic reaction are synthesis reactions requiring energy and storage of precursor metabolites. This is all reviewed, guys. Many anabolic pathways are the reverse of what? Catabolic pathway. That's what I said. You can break things down, or you can take those precursor molecules and build them back up. Otherwise, like I said, if you couldn't do that, since you have to have glucose for glycolysis, could you survive on Atkins? Could you survive just on Atkins?
Yes.
Just on protein, if these pathways weren't reversible?
Well,
No.
Atkins
No.
isn't just protein.
Yeah, or fat protein, let's say just protein, whatever.
Okay.
Super protein, there's a new one out there, I know there's a new one every week. I know guys just on, just protein. But could you survive on any of those if these pathways weren't reversible?
No.
No,
Not if they
because you
were.
need those carbohydrates for stuff, so you gotta be able to build those sugars back up. You wanna build them up and put them back in, they're signaling molecules, right? And that's the gist of what you get out there. And like I said, here are all the precursor metabolites, here's where you get them, and this is what you can do with them. And what I want you to know about the pentose phosphate pathway right now is that you use it to make what? Nucleic acids, nucleotides. That's where you take these 6-carbon sugars and you turn it into a 5-carbon sugar, ribose. And you use ribose to make what? Nucleotides. That's the big one. You get some energy out of it, you can do some other stuff.
What is it called again?
It's called the pentose phosphate pathway, or the pentose shunt. They don't call it that anymore. Again, why does this make sense right here? And we're gonna look at this, we'll look at this later on when we get to the genomics part. I wanna go through that really quick. Do you wanna make enzymes you don't need? What's the point? It's a waste of what? Highly energetic, to take a lot of energy to make a lot of these enzymes. You don't wanna waste the energy or the parts. Cells use allosteric sites of enzymes to control enzyme activity. It's all about, what's the term I said? Regulation. That's the main part. Cell-directed these are the pathways that go both directions. Okay, this you need to know, especially research, when you're doing research, you already know this. How do you control gene expression? How do you control, okay, 2 types of regulatory mechanisms. Enzymes are proteins. How do you make proteins? Let me back up.
Amino acid.
You make them again, but we're going past the macromolecule part. In the cell, how do you make them? Transcription and translation, right? That's going to give you an enzyme eventually. So you can control gene expression AK, you don't make the enzyme if you don't need it, so you don't transcribe the gene, you don't translate the messenger RNA. So you can transcriptionally, write this down, guys, I'm gonna write this down, and translationally control gene expression, or enzyme production. And translationally. You can either not transcribe it, or you can control translation, not translate it. The thing is not that bad. Think about it backwards. How can you control protein expression? You can control it at the transcriptional level or at the translational level. It's not that bad. What do you think is the easiest way to do it? Transcriptional level. Just don't transcribe the gene. That's the easiest way to do it. Control metabolic expression. Cells control the activity of protein. So let's say you made them, then you could still have another level of regulation, which is going to be what? Allosteric regulation. You can turn the enzyme on, you can turn the enzyme off. Okay? Whoa. Don't forget about the calcium inside. What I want you to know about that? What I said, what did you know about that slide?
I'll go over that.
Good. Well, yeah. Sort of.
That's it?
Then all these things are reversible. That's kind of what I wanted to show right here. Integration cellular metabolism. I can take nucleic acids and I can break them down to nucleotides and I can put them over here and stick them into what? Glycolysis and then pyruvic acid and that's big energy. Or I can take P3P, pull it out, run it back up here, make nucleotides, and then make nucleic acids. These are all reversible.
Reverse.
And it just depends on where they're going to go into the cycle. I mean, if this is a junior level microbiology course, we have to memorize all those pathways and what goes on for that. This isn't, so I don't want you guys to worry about that. All right, you all good on this metabolism? You should be, since it's the 27th time. Big one over. If you all need a good grasp of this for this test, guys. We'll ask questions. Who's taking the test again? Am I taking the test? You're taking the MCAT, right?
Already.
You already taken it? Should have been some of this stuff on the MCAT, was there?
Yeah, a lot of like controlling metabolism, like if you have this like gluconeogenesis, stuff like that.
Yeah. So this on the MCAT is also on the
Hesse.
Hesse and what?
Teas.
Teas. Can I call it the Tissy? That covers both of them?
Yeah.
So the Tissy cat. Right? And they're on there. Right. Yeah, I was gonna do it. One of my friends went to Judith for the MCAT for people. And I just went in and took it blind. I said, all right. All right.
I've heard that Jesse's good with the my best friend was
All right.
in
So we'll go through this. I'm probably going to learn more of this part of the text than the other part. So microbial growth, what does that mean? An increase in population numbers. Microbes is numbers, and us it's growth is what? Huh? Huh? Yeah, the growth is an increase in size, yeah, microbes. Well, this, I have that anyway, and I'm congested. You know, between the two, I can barely hear a train coming. Okay, physical, let's just go through these all at once. Let's just go through these real quick. We got plenty of time. You guys should know all this. I don't want to go through all this. I don't want to go through what are the 4 targets, main targets, guys? Membrane, cell wall, protein synthesis, and what? Metabolic pathway. Those are the big targets, right? The last target is going to be DNA synthesis, stuff like that. The problem with that is it's very conservative. Very hard to target something without making a
Can you repeat membrane, cell wall, and then the other two were?
Well, what are the targets? What
I
are
know
the physical things? What are the things that you're going to affect here?
I know those two.
Cell wall, membrane,
DNA.
metabolic pathways.
Metabolic.
And then, protein synthesis.
Oh.
But that's all gonna be, but that all affects this right up here. Where they can live, where they can't live, okay? Gets too cold, the membranes get too what? Rigid, okay? Things can't move in and out of them. It gets too hot, they get too fluidic, they become what? Leaky, stuff leaks out. And this is just a growth curve, you should see this. This is just telling you what? All microbes have a particular what? Temperature they grow best at, and it's all based on their enzymes for the most part. All right. Just know these ranges. Don't know them exactly. I'm not going to ask you, an organism grows at 44 degrees centigrade. What is it? What would it be? It could be A and B, right? Just know this one. I mean, know the extreme one. Thermophile is the hardest one. But let me ask the question. If an organism is pathogenic, it is probably going to be a mesophile, right?
Mm-hmm.
You find an organism growing in the ice sheets in Canada, it's probably going to be a psychrophile. And then you've got facultative psychrophile. We're not going to go into those for this class. An organism growing in a hot spring in Yellowstone will be a hydrothermal. An organism growing in the hot springs in T or C would probably be a thermophile. Could be both, but yeah. I think those hot springs up there are about, yeah, it could be both. Probably would be a thermophile. All right. Now these right here, these are pretty straightforward. But I could ask in combination, like I said, that organism growing in that hot spring in Yellowstone is probably going to be a hydrothermophile and a acidophile, right? Because most of those hot springs have very low pH as well. They usually have sulfur blowing through them, so they keep sulfuric acid. If an organism were to grow on you, would it be a neutrophil, an acidophil, or an alkophil?
Oh.
Growing in on you, what's to grow in and on you? What's your
Neutrophile?
pH up? What's your old pH up there? 7.3, right? And what is 7.3?
7.3.
7.3. So what would you be? Are you going to be an acidophile? I'm sure alive or not. Is it going to be an alkophile? Nope, it's going to be a neutrophile. So both pathogens are going to be mesophiles, neutrophiles. All right. Water requirements again. Endospores, we know the difference. Osmotic pressure is what? What protects it from osmotic pressure? Cell wall, not the membrane, the wall. What is hydrostatic pressure? Pressure being exerted on an organism by the weight of the water above it. Where's the only place you're going to find baraphiles? You guys should know how. I don't know how to sound. You should know.
Deep sea. Deep sea.
Deep ocean. That's the only place on the earth you're going to find it. A halophile is what? Let me go to the next slide. It's better. So what's a halophile? Halo means salt. The halophiles mean salt, right? If you are an extreme halophile, you need a lot of salt. 15 to 30% is huge. Okay. If you're a regular halophile, you want somewhere around 5 to 10. Okay. If you're halotolerant, what does that mean?
You can grow either.
You can grow there, you can tolerate it.
It's better.
Yeah, and you'd probably be. So what would Staph aureus and Staph epidermidis be? They're usually halotolerant ones, actually. We're not that salty in that way. All right. Hydrostatic pressure, we talked about that, where you're going to find those. And why they need them. They need that pressure to hold everything, to evolve over time. They need that pressure to maintain a three-dimensional structure of their enzymes. Okay. Energy, what are these right here? Let me just open up this thing. So I'll ask a few questions on this. And people always think this is easy and we get on the test and we don't have the little box here and they freak out. Okay?
That's gotta be me.
And to me, when I learned this, it was easier for me to remember what it isn't than what it might be. Okay? If it's got photo in it, then it's what? It uses the sun for photosynthesis is energy, right?
Yes.
Good. So if it doesn't say anything about sun, then you know it's gotta be a what?
Chemo.
Chemotroph, right? Auto means it gets its CO2, its carbon from CO2, okay? So if it doesn't get its carbon from CO2, can it be an autotroph? If it gets carbon from anywhere else but carbon dioxide, can it be an autotroph?
No.
No. So those are the two to remember. You look at those two, and if it doesn't have one of those two, then it's gotta be what? Gotta be the other
Chemo
one.
and chemo heterotroph.
So heterotrophs get their carbon from some type of molecule. You know, you can be a chemo organotroph, you can be a chemolithotroph too. Okay, but we're not gonna go into that, we're just gonna go into chemoheterotrophs. Chemoheterotrophs get their energy from where?
Chemicals.
Breakdown of some chemical compound, right? They get their organic stuff from some organic molecule, same thing. Where am I? Autotrophs get their carbon from
Carbon from CO2.
CO2. So,
Where do heterotrophs?
so you have an organism that's growing close to the surface of the ocean. Okay?
Okay.
What would you think it would probably be?
Photo, auto?
Could be a photoautotroph. Now, they're only gonna have some answers in there that would make sense, so they'll have some other wrinkles on it. But since it's saying it's growing close or on the surface, that's probably telling you it's a what? It's a phototroph, right? It's growing somewhere up there.
So what about hetero? What does hetero mean?
Okay, you find an organism that's growing deep down in a cave. That has an extremely high carbon dioxide content. What would that probably be?
Chemo auto.
Good, chemoautotroph. Okay, let's look at air, you need to know these. What does facultative mean? You can use it, but it probably would rather use not have it or something like that. Facultative means you can use it. Obligate means you are what? You're obligated to use it, or be away from it, whatever it is. Okay. So if you're an obligate aerobe, usually it's called aerobes, you have to have oxygen. We are obligate what? We're obligate aerobes, right? We have to have oxygen. Otherwise we what? And why do we need that oxygen? And what is that called? Oh, that's right. Yeah, what is it called? Terminal.
Reaction? Or
No, terminal, what are those things that come bouncing around that we moving around the electron transport chain?
terminal.
The electron transport chain?
Electron acceptor.
Terminal electron acceptor. Alright, if you are a micro aerophile, you need oxygen, but you only need what? Little bits of it. Okay, can't go back to the micro aerophile. So if you see something that's growing in relatively high CO2 and not just CO2, it's probably a micro aerophile. They usually like high CO2 also. If you're a facultative anaerobe, you what?
You're okay with it, but you don't need it.
You'd rather have oxygen, but you can shift pathways and you can live without it, right? Which one are you gonna grow better at? And go back to the yeast and the E. coli. If you are a facultative anaerobe,
Oxygen.
you're gonna grow better in oxygen than without it. Yeah, they would rather have it because they make more energy that way. Aerobic respiration, no matter what, generally makes more energy than anaerobic. If you are air tolerant, that means what? You don't need it, you don't use it, but it's not gonna bother you. If you are an obligate anaerobe, that means oxygen is absolutely what? Toxic to you, okay? Because you do not have the enzymes to break these things down. The only two I want you to know is, let's see, those three. Catalase, you should know that, we've gone over that 100 times, right? Okay.
And the opposite anaerobe. Wait, I get confused.
That's one of the tests, take your time.
Can they be pathogens? Because there's like,
Yes, they can.
there's like oxygen.
Yeah, but they get down inside the tissues, okay? So here's an example, that's a good question. Can an obligate anaerobe be pathogenic? Yes, now it depends on how they work. Clostridium C. diff is an opportunistic one. Your gut is pretty anoxic down in your colon. Okay? Another one is gangrene. Clostridium perfringens. The spores, they fuse in wars a lot. A bullet wound, what happens to a bullet or a knife wound if it goes into muscle? What happens to the wound tract? It goes in, but what happens behind it as it's going in? It usually seals up to some extent. I mean, it's still gonna bleed, don't get me wrong, but usually never seals up to some extent. If those spores get inside of that wound, in it's an anaerobic space, they'll germinate, cause gangrene. So the answer to that question is yes, you can do it. Catalase breaks down hydrogen peroxide. Peroxidases break down hydrogen peroxide. Superoxide dismutase, what I'll probably would ask on something like that is, you find an organism that does not produce solid. It's probably going to be a what? So that's one of the big ones. It's probably going to be an anaerobe. If it doesn't make superoxide dismutase, it's probably going to be an anaerobe. That's all, I'm not gonna ask you anything else. I could put something on here, and it has organism in tube C is,
Tolerant,
No, it's facilitated.
oh no, yeah, it
yeah,
like.
take your line, why do you think it's facultative?
Because it can go to your order with better working.
Right. So it's growing all over the tube, right?
But it's
But it's
attractive.
growing better where there's what?
There, oxygen.
So those guys are gonna grow better usually where there's oxygen. All right, the pheromone chamber is the catalase. Anabolism, you know what nitrogen fixation is? What is nitrogen fixation? Not that you're fixated on nitrogen. Know what it is. What is nitrogen fixation?
changing nitrogen to something that can use
You're gonna make nitrates or nitrites, something that can be used by plants. Plants can't use elemental nitrogen. All that's all we need to know. Growth factors, trace elements are what? They're required, but they're only required in what? Small amounts. One of the big ones is selenium. That's my favorite one. Right? The difference between trace elements and growth factors is what? It's not just they can't synthesize them. I can't synthesize selenium or magnesium either. But what's the key, the other key part to it? Which differentiates them between trace elements. Organic, that's the difference. Growth factors are organic molecules. Okay, somebody you need that's organic. A lot of vitamins, things like that. All right. Okay. Antagonist, another difference is you should know that antagonism means what? Somebody benefits, somebody gets hurt. Right? Virus through any cell, right? Synergistic means they can live by themselves, or they work together, they do what?
better.
Much better. Right? Symbiotic means it's an obligate relationship. There's a symbiosis going on, they've evolved where they have to have each other. Right? They cannot survive on their own. And we'll talk about the difference in medical there. And biofilms are just what?
Absence of
Look into it. Right. Biofilms are These groups of bacteria get together, they start secreting a matrix, and they start cooperating. And they send out these quorum-sensing molecules, and those molecules sense what's going on, and they can actually change the metabolism, the biochemistry. So they start working together. I should show you a picture in the class of the platform. An inoculum is, this one, a lot of this is just nomenclature, right? This one. The sample, right? An inoculum, right? Sample of microorganisms. Medium can be liquid, it's called a. If you put agar in it, it's called a. Called agar. This is pretty straightforward. If you take a sample from a person in a clinical setting, it's a clinical sample. If I take something from the street, it's an environmental sample. If I pull something out of the fridge, it's a
Store.
store sample. I can't imagine I would ever ask a question like that. Cultures, you have the cultivated microorganisms or the microorganisms that you are cultivating, not cultivating. And a colony is what?
Their
That's the
growth.
visible culture on the surface of solid media. Key to that one is solid media. You don't have colonies in broth, do you? And those colonies all come from what? One, and what is the term for those things? I have X number of blank. Units is in it. It's making a colony, so you got a colony in it, you got units in it. We're missing one word. Good. CFUs. That's how you express things. And a CFU is just a bacteria. If I have 5,000 CFUs, that means I have 5,000, which means I have 5,000 bacteria. That's just how they start to refer to them. So X CFUs per mil. Then that's what in that lab. You should know if your culture is, it comes from a what? A single progenitor, and the progenitor is called a colony forming unit. Alright. Aseptic technique just means you try and prevent, aseptic technique is to prevent contamination of your sample. Okay? They like to use the word pathogenic contamination, but it doesn't matter. It's just contamination. Aseptic technique. What are the two ways you can isolate bacteria? Street plates right here where you just do what? You streak them out, you try and separate them out in the individual one. Then what would you do next if you wanted to get a pure culture? In a broth, usually draw it up, and then what would you do after that? To make sure you re-streak it and make sure you have a single colony type on there. All right, what's the other one we talked about? I don't worry about protozoans. I don't know why this guy. Okay, I don't know why that one got away. Let's go back to the. What are the different types of media? Because you need to know this. Let's find some cool questions around this book. I like that. So, define, okay, agar is just what? You should know what agar is. It's made from red algae, it's a semi-gelatinous stuff, it's semi-solid at room temperature. But the key components to are, it cannot be broken down by bacteria, so they can't eat it. Okay? It's liquid at high temperature, so you can pour it, but it's solid at room temperature, and it's solid at body temperature too. And thirdly, you can do what with it? It's not on that one, but I told you about it. We'll talk about it later on. What else is unique about the agar? Why does it allow you to grow bacteria?
Because it has nutrients in it.
The what?
Does it have nutrients in it? So
You can put the nutrients in that you need. Good, and that goes down to these things down here. Define your synthetic media, the exact chemical composition is known. So if I said you have a media that has 20.5 grams of potassium carbonate, 0.25 grams of calcium carbonate, 0.5 grams of sodium phosphate, 0.25 grams of sodium chloride, 8 grams of glucose dissolved in agar and 1 liter of water. What type of medium would that be? Come up there.